talking to the video now. We worked a few review problems to start with here, so I'll let you see them on the board if you want to try to work those. And then we're about to answer questions from the homework final review. Questions on that? Nora, are you okay on that one?
Yeah.
Okay. Well, don't use your sweater, Nora. Okay, questions on homework, final review B, or anything you would like to see clarified?
Will you do number 1C?
The 1C. So did you have, okay, so this is where we're looking for the equation then of the sinusoidal curve. So if we have 1, 2 is going to be a minimum, and 11, 8 is going to be maximum. And this is supposed to be some kind of sinusoidal curve. So it's a sine or a cosine. So do you want to think of it as starting here at a low point or starting here at a high point?
Low.
The low, okay. So is that going to be a positive or negative sine or cosine if it starts low? Okay, so it's going to be a negative and it's going to be a cosine. Okay. And because we're starting it at x equals 1, that means we're going to have an x minus 1 in parentheses. So those three things are decided together by where you start. Now the order you do the rest of this in doesn't really matter, but we can see that we have a high and a low, so we can find our amplitude, that value of A that's going to go in front here. If we take top, the high minus the low, the max minus the min divided by 2. So that's going to be the y value 8 minus the y value 2 divided by 2. So that's going to be 6 divided by 2 is going to be 3. And once we know the amplitude, we can find the midline by counting up from the low point. So the low point has a y value of 2. If we go up 3 from there, that's going to put that midline at 5. And so that means we're going to get a +5. That's going to be our translation vertically. So now we got everything except for the hardest one. So the hardest one is to figure out that B in general. So in general, our B is going to be the natural period. And is this in radians or degrees?
Radians.
Radians, because we don't see any degree bubble. So the natural period is going to be 2 pi. And we're going to have to divide that by the actual period. So to get the actual period, from a low to a high is half of a period. Because this is going to go up to a high point and then it's going to come back. And once it gets back to where it starts, that's going to be the full period. So from low to high is half of a period. So if we take the x value 11 here, minus the x value 1 there, so 11 minus 1 is 10. That's our half period. So if we multiply that by 2, then the period of this graph is going to be 20. And so the B is going to be the natural period 2 pi divided by the actual period 20. And that's going to make that be a pi over 10. Okay. What else? Okay, so we're clear. Final is going to be Friday morning. And if you want to do extra practice, you can still come in after school today, after school tomorrow. And we can do some more practice problems. All right. Anything else before we start looking at tangent and how to graph it? Okay. So we are going to to talk about, so this is the tangent function. So we're gonna try to make a connection between how we understand tangent from the unit circle, and then convert that to how we're gonna actually graph a tangent curve on an XY axis. So I'm gonna look over here at our unit circle, and this is we're gonna be thinking in radians here. So this is gonna be 0, and this is gonna be pi over 2. And then at the same time, we're gonna try to figure out on an XY axis, what are those implications? So what's the significance, the importance of how we understand the tangent on the unit circle compared to what we're gonna get in terms of the graph of that tangent function. Let me get some different colors here that I can use. So we know that if you look at any right triangle there on the unit circle, we have said that, let me make sure that's a unit circle, so that point there is 1, 0. And so what we know then is that the x coordinates, so if this is our angle theta, this side length on the right triangle is the x coordinate of this point, and this side length is the y coordinate, and that hypotenuse is 1. And so we know that the tangent is going to be opposite over adjacent, so that's going to be the y over x, which when you look at that as, if you imagine this line going through the origin, so kind of take a step back away from the unit circle and look at that more globally, then that line through the origin is going to have a slope of, the rise is going to be that y, and the run is going to be the x, or the delta y, delta x. So what we see is that the slope of that line through the origin, where that angle, where that line makes an angle of theta with the x-axis, its slope is exactly the tangent of that angle. Does that make sense? So kind of a different way of thinking of a tangent is it's the slope of the line through the origin. And you just figure out what the angle is by, you're talking about the angle that the line makes with the x-axis. So that gives us maybe some other ideas here. So as we go to try and graph this, we can see, for example, that when we are at this line of 0, when the angle is 0 radians, then the slope of that horizontal line is going to be 0. And so if we go to graph y equals, I'm going to call it not tangent theta, but tangent x, so we're thinking, we're inputting the angle 0 radians, and the tangent of that is going to be the same as the slope of the line through the origin. That is going to be 0. Now we can see that the one that we like to know, that you want to be asked on a test question, is going to be what's the tangent of pi over 4, because from our other understanding of what a tangent is, that it's the sine over the cosine, we know that at pi over 4, sine of pi over 4 is square root of 2 over 2. You with us here, Ashley? Yeah. I'm not believing that, but I'll go with it. And the cosine of pi over 4 is also square root of 2 over 2, which means the tangent of pi over 4 is 1. So what we have then now, if we know that the tangent of pi over 4 is 1, if we go to pi over 4, then we know the tangent curve is going to have a y coordinate of 1. That makes sense? Now, it gets interesting as we make our way, so as we kind of sweep our way along here, looking at the slopes of those lines going through the origin. Here's 0, at pi over 4 it's 1. As we get steeper and steeper, what are the slopes doing?
Increasing exponentially.
Not necessarily exponential, but they're definitely increasing. So it's not gonna quite be exponentially, because it won't be an exponential curve, but it's gonna be increasing fast. Yeah, it's not gonna be a straight line. So, you know, it took us all this time, you know, to get to 1. But then they're gonna start getting really, really steep, and we say that a vertical line has no slope. But what, if you were thinking this like in the language that we've been trying to start talking about as a limit, as that angle approaches pi over 2, these slopes of the lines are getting bigger and bigger and bigger. We could say they are approaching positive infinity. You with me there?
Yeah.
So that idea of, and we would say the limit as x approaches pi over 2, and we're approaching with angles that are a little bit less than pi over 2. So you remember how we say that we're approaching pi over 2 with numbers that are less than that? What we call that? Evidently not. So that we would put the negative sign there, we're coming in with numbers that are smaller. So we're approaching pi over 2 coming in from the left, using angles that are less than pi over 2. We're coming from the 0 side, right? Not from the side where these angles are bigger, from the pi side of that. So this, we would say, is a left-hand limit. We're coming in and approaching it this way. Then these slopes are getting bigger and bigger and bigger. They're going to be approaching infinity. So what that means in terms of a graph, if this curve is going to approach infinity, means it's going to be a vertical asymptote. So it's going to blow up and take off going up. That make sense? Now, let's suppose we go the other way. So what if we head out here towards maybe negative pi over 4? So now we reset back to 0. So here we're looking at this angle. Now we're going to come down in here into quadrant 4. So here's where the angles go negative. You with me there? And so as we work our way down here, when we get to a negative pi over 4, then the tangent of a negative pi over 4 is going to be a sine of a negative pi over 4 over a cosine of a negative pi over 4. Well, they're both going to be square root of 2 over 2 again, except that in quadrant 4, sine is negative, whereas the cosine stays positive. And so if it's a negative over a positive, then this is going to be equal to negative 1. So the tangent of a negative pi over 4 is going to be a negative 1. And so we're going to look here at a negative 1, and we're going to get this point right here. And you can see, I hope you can see, so as we look at lines here, they're falling from left to right now, these lines going through the origin. So once we pass the horizontal here, which we're thinking of as angle 0 radians, as you move your way down into quadrant 4, these slopes through the origin are now falling from left to right. They all have negative slopes. As we get closer and closer to the y-axis, as this approaches vertical again, these are getting to be steeper and steeper lines with negative slope. We're going to say that limit, so let me say, let me come back to this, we're going to say that is going to go to infinity. If we are looking at the limit as x approaches negative pi over 2, so we're coming in this way, and we're coming now as we approach a negative pi over 2, are we coming in from the left or from the right? From the right. Okay, so these are, so we're going to put in our notation here for limits. We're going to say to show we're coming in from the right, we put a little plus sign there. And this is our tangent of x. And we're gonna say this is approaching what? Negative infinity. So still the same vertical line that we had coming this way, but here we were coming in with positive slopes because the lines were rising from left to right. This way we're coming in from the negative side because these are lines that are falling from left to right. And so we're gonna say that limit is gonna be a negative infinity. And so what that's gonna give us at pi over 2 is, again, a vertical asymptote, but this time we're going to dive down and go to negative infinity. That make sense? So what we get is this thing is kind of reminiscent of a cubic, right? Kind of is suggestive of y equals x cubed, but it's not the same graph because y equals x cubed doesn't have these vertical asymptotes. So this is kind of pinned in between these two vertical asymptotes. Whereas a y equals x cubed, it just keeps going over and up and over and up and over and up. But the shape is kind of reminiscent. Now, words that I'm going to use with a tangent versus a cotangent, which is coming here in a moment, is I'm going to say it's going to start in the middle. So a tangent without any translation or reflection or vertical or horizontal stretch or shrink. Our parent function for tangent is going to start in the middle. And then I'm going to say you're going to go, notice that these important values, these points that we find, are again every fourth of a period, just like we saw with sine and cosine. Okay, well, I should say, this is going to repeat itself when we come back to that idea of a period. So once we come over here, we're just going to repeat what we're doing down in quadrant 4 here again. So what we're going to find is at pi over 2, we have the vertical asymptote. That's like 2 fourths. When we go to 3 pi over 4, and then pi, and then 1 1/4 is 5 pi over 4, and then 6 fourths is going to be 3 pi over 2. So let's see what happens. This is what we're going to start talking about, is where is this tangent? And now maybe we can think of this more like we did before as sine over cosine. So we're going to kind of shift the way we're thinking of this now, maybe moving away a little bit from the unit circle idea and more to, it's going to be a fraction sine over cosine. A fraction is going to be equal to 0 when its numerator is 0. And you remember where sine is going to be equal to 0. Yeah, it's going to be at 0, pi, 2 pi, 3 pi, and so on. So it's going to be at multiples of pi. So thinking about your sine curve, which remember does something like this, and these are going to be multiples of 2 pi. So 0, pi, 2 pi, negative 2 pi. So where sine is 0, this tangent function, which has sine in the numerator, will also be 0. So it's going to be at the multiples of pi. Question more?
So does that mean that, like, after every asymptote, it just like keeps?
It repeats itself. Yeah, exactly. So at pi, we're going to get another 0 there.
Okay.
Now, a fraction, we know from our domain questions we were doing for review, a fraction is undefined when its denominator is 0. So since a tangent has cosines in the denominator, it's going to be undefined when cosine is 0. And if you remember what the cosine curve looks like, you know, it does something like this. So whereas the sine curve is 0 at multiples of pi, pi, 2 pi, 3 pi, so on, the cosine curve is going to be equal to 0 where?
Pi over 2.
Pi over 2,
3 pi over
3
2.
pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2. I call them the over 2's, right? So it's going to be pi over 2, multiples of pi over 2. So where we get the denominator to be 0, this is undefined. And where it's undefined, that's going to be a vertical asymptote. So at the over 2's, 3 pi over 2, at negative, we see negative pi over 2, and negative 3 pi over 2, and so on, you're going to get another vertical asymptote. Now, so the way I'm going to describe it is we're going to go you know, it's gonna start in the middle, we're gonna go two, I call them critical points, but that's my made-up term for it. Two critical points to the right asymptote, two critical points to the left asymptote. Now, if it hasn't been reflected, we're gonna go one critical point over, and then we're gonna go up to one. So we're gonna go one critical point over, and we're gonna be back to one. So remember, 5 pi over 4, we can think of in several different ways. If we think of tangent as being sine over cosine, then at 5 pi over 4, we get sine of 5 pi over 4 over cosine of 5 pi over 4. Well, the reference angle is pi over 4, so that value, without worrying about the positive or negative sign, is gonna be what for a sine and a cosine?
Square root 2 over 2.
They're both square root of 2 over 2. 5 pi over 4, remember, is down here in quadrant 3. In quadrant 3, the sine is,
Negative.
and the cosine is,
Negative.
so a negative over negative is gonna make it positive 1. So that one critical point to the right is gonna be a positive 1. At 3 pi over 4, we're gonna be in quadrant 2, where the sine is
Positive.
and the cosine is,
Negative.
and so it's gonna be a negative 1. And then it's gonna repeat itself. And it'll do that in both directions. So it will continue this same shape, but it just repeats itself over and over again. Okay? So, what is the period of a tangent curve? What's the horizontal distance you travel before it starts to repeat itself again?
Just pi.
Just pi. Yeah, so pi over, in between those asymptotes, from pi over 2 to negative pi over 2, that's a distance of pi. So sine and cosine have natural periods, we say, of 2 pi, but a tangent curve, and we're gonna see this for a cotangent as well, have a natural period of pi. Now, we talk about amplitude a lot with sine and cosine. And that's gonna be the max minus the min divided by 2. Well, what's the maximum value of a tangent curve? And it goes to infinity, it doesn't have one. And same with a minimum value. So it doesn't make sense to talk about amplitude. That's not a reasonable question to ask. So we won't. So the amplitude, it's just not a relevant question. Since it doesn't have a maximum and it doesn't have a minimum, we can't give a number answer to what is this amplitude gonna be. It's gonna be infinite in both directions, always. Okay? Okay, so here's how we're gonna do it with a tangent curve, and these are the words I'm gonna use because, like I said, with a tangent compared to a cotangent, these are the ones that people have the most difficulty with because they are similar enough yet different that they are really easy to get confused. So I will talk about a tangent curve starting in the middle, just like we did with a sine curve. It's gonna start at the origin until we start translating and reflecting it. Then we're still gonna have these important points that we're gonna graph. We're not gonna graph lots of points. We're always gonna look for what happens at, well, it's kind of 5. It's every fourth of a period. So you got beginning, ending, middle, and then one critical point on either side. So in a tangent curve, it's always gonna start at in the middle. See what I mean? That's a little long for one blink. It's gonna start in the middle. 2 critical points on either side, we're gonna have beginning and ending asymptotes. 1 critical point on either side, you're gonna go up to 1 or down to negative 1. So you gotta try to remember that, because I'm gonna change that up for a cotangent. Now, the reason for that is when we think of this as a fraction, it's gonna be 0 when the numerator is 0, and that's gonna be at the multiples of pi, where sine is equal to 0. The asymptotes come from where it's undefined, when the denominator is 0. And that's gonna be where cosine is 0, and that's at the over 2's. Pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so on. It is periodic, so it repeats itself over and over again. Its period is pi. Okay, burn that into your brain, into that picture, and we're gonna now, in a much shorter version, we're going to see what the graph of cotangent looks like. So we are going to graph And cotangent, so, I don't know, have you seen this before? Is this the first time you've seen cotangent? It might be, I don't think you talk about this in geometry or anything. So, there are, in fact, we're gonna get 6 total trig functions. So we know sine, cosine, and tangent. And we can define them in terms of our right triangle from SOHCAHTOA. You know, the sine is opposite over hypotenuse, that cosine is adjacent over hypotenuse, that the tangent is opposite over adjacent. We can divide it in terms of the unit circle, that the sine is the y-coordinate of a point, and the cosine is the x-coordinate, and the tangent is the sine over the cosine. We define it in terms of, back in terms of sine and cosine. Well, cotangent is the reciprocal of tangent. So this is the whole word, cotangent, but it's abbreviated COT. So a cotangent can be known as several things. It is the reciprocal of tangent. So it's the reciprocal function of a tangent and cotangent. Now it's gonna have, we'll talk more about this on another day, but we'll talk about, you know, how we talked about the cofunction properties of sine and cosine. That the sine of a 20-degree angle is the same as the cosine of a 70-degree angle. It's the complement, yes. So a sine of one angle is the same as the cofunction of its complement. Sine of 20 is cosine of 70. If you looked at those table of values we've memorized, the sine of 30 degrees is 1/2. The cosine of 60 degrees is also 1/2, because 60 and 30 are complements of each other. The sine of 45 degrees is
5 root 2 over 2. Sine of what?
It's, so that's the angle in radians, but the sine of 45 degrees is, oh,
One?
no. Sine, start small, go 0, 1/2 square root of 2 over 2 square root of 3 over 2, 1.
That's what he said.
Yeah, I said root 2 over 2.
Oh, you said root 2 over 2? I thought you said pi over 4.
I said pi over 2, and then I was like, oh no, root 2 over 2.
Oh, okay, I didn't hear I'm sorry about that. Then you were correct. I stand corrected. Yes, sine of 45 degrees is square root of 2 over 2. The complement of 45 degrees is 45 degrees, and so the cosine of 45 degrees is also that, because they are cofunctions. Well, that same property is gonna hold with tangent and cotangent. The tangent of one angle is the same as the cotangent of its complement. Okay, and we'll get others too, but I don't wanna get ahead of ourselves. So we can also think of this because it is the reciprocal of tangent, and tangent is sine over cosine, then the reciprocal of sine over cosine is cosine over sine. And I know it gets really confusing and easy to mix up when you start, but it has to become kind of second nature. So we can think of cotangent as being the reciprocal of tangent, as being cosine over sine, especially if we're thinking our unit circle definition, you know, that we're going on the unit circle, we're getting the x and y coordinates. In terms of SOHCAHTOA, because the cotangent is the reciprocal of the tangent, and tangent is opposite over adjacent, then the cotangent must be
Adjacent over opposite.
the adjacent over the opposite. So all these are ways of knowing what the cotangent is. It's all of these things at the same time. The reciprocal of tangent is cosine over sine. It's adjacent over opposite, depending on how we want to think about it in a given situation. Okay, so let's talk about graphing this thing. Now, I'm going to suggest here that we think of it as cosine over sine, and we're going to first find where is this equal to 0? Where are the x-intercepts going to be? And because cotangent is a fraction, and a fraction will be equal to 0 when its numerator is 0, the question becomes, where is cosine equal to 0?
No. Multiples of pi.
Multiples of pi over 2, right?
Multiples of pi over 2, right? Let's go back to unit circle, okay? So cosine is the x-coordinate. Where on the unit circle do we have x-coordinates that are 0?
At
Pi over 2,
3
3 pi over 2,
5
negative pi over 2, negative 3 pi over 2, and so on. Those are the places where our x coordinates are 0, which is gonna be where the cosine is 0. So I'm gonna go and I'm gonna mark here at the over 2's is what I call them. We're gonna put x-intercepts. So here's pi over 2. I'm gonna put an x-intercept down. So I'm gonna go over, there's 3 pi over 2, and I'm gonna put an x-intercept. Here's negative pi over 2, and I'm gonna put another x-intercept. And actually, I'm gonna go ahead and mark that. So here's negative 3 pi over 2, and I'm gonna put an x-intercept down. So already you can see it's different than the tangent graph, right? Because the tangent, because it had sine in the numerator, it was gonna be 0. Its x-intercepts were gonna be at multiples of pi, because that's where sine is equal to 0. We're gonna get vertical asymptotes when the denominator is 0, which makes the actual cotangent curve undefined, and that's going to occur where? Where is sine equal to 0? At the multiples of pi. So at 0, pi, 2 pi, negative 2 pi, so on. So 0 is going to be a vertical asymptote in the cotangent graph. Pi is going to be a vertical asymptote. Negative pi is going to be a vertical asymptote. Okay, so far. Now, like we did with our, so we're starting to get a shape for this. Let's talk about what happens now in between a couple of vertical asymptotes. So here we have a vertical asymptote at 0, and here we have a vertical asymptote at pi. We know that it's going to be equal to 0 at pi over 2. So what's going to happen at our fourth, at the halfway points in there? What's going to happen? Let me put this more. There's pi over 2. Here now is pi over 4, and this is going to actually be pi. Here's 3 pi over 4. So now we're looking for these places. So at pi over 4, remember this is cosine over sine. The cosine of pi over 4 is square root of 2 over 2. The sine of pi over 4 is square root of 2 over 2. So the cotangent of pi over 4 is square root of 2 over 2 over square root of 2 over 2, which is 1. Okay, so we're going to get just 1. And so, just like we did here, right? Tangent at pi over 4 was also 1, because if it's equal to 1, then its reciprocal is still going to be 1. Okay, now at 3 pi over 4, we're still saying cosine over sine. The reference angle is still pi over 4. We're now in quadrant 3, right? Here's our 3 pi over 4 over here. Our reference angle is still pi over 4. So we're still going square root of 2 over 2 over square root of 2 over 2, but now we're in quadrant 2, so that changes things because why? Cosine is negative in quadrant 2, but the sign remains positive. So now we have a negative square root of 2 over 2 over a positive square root of 2 over 2, which makes the cotangent equal to negative 1. And so same values that we got for the tangent and the cotangent, but a little different order. This is why this is, I think, so hard for students when they're first learning, is they're just similar enough yet different that it becomes sometimes hopelessly confusing. So I'm going to use the words to try to distinguish those. I'm going to say that a tangent curve starts in the middle. I'm going to say that a cotangent curve starts with an asymptote. Tangent starts in the middle, like a sine curve does. Cotangent's going to start with an asymptote. We're still going to have our fourth of a period, so we're still going to mark our fourth of a period over. So tangent, after starting in the middle, is going to have its asymptotes 2 critical points right and 2 critical points left. A cotangent curve is going to begin and end with an asymptote, and it's going to have its 0 in the middle, 2 critical points in. A sine curve is going to rise from left to right. A cotangent curve is going to fall from left to right. Okay? That's kind of fun, I think. Fun, I guess, is up to the individual. It's going to still be periodic or repeat itself. I think it's kind of cool when you do the half periods on either side. So you get, if we just do that part of it, I think that looks kind of cool. That's, just me. It repeats itself forever in each direction, so it's periodic. What is its period? Yeah, the distance between those asymptotes is still pi. So both tangent and cotangent have periods of pi, and they don't have an amplitude because they're infinite. Okay. Well, burn those images in your brain. These are gonna be our new parent functions. And then we're gonna try to throw in all the other stuff that we do. We're gonna do our reflections, we're going to do our translations, we're gonna do our vertical and horizontal stretches and shrinks. Now, what we will see with our horizontal stretch and shrink is gonna change that period. Just like we saw, this is the B now, so when we look at things like y equals a tangent of b times x minus c plus d. And same thing with a cotangent. The a, our amplitude, well, what we're gonna see, where we're gonna see that is in these points right here, in the cotangent curve, and these points right here in the tangent curve. So when we, in a tangent curve, if this was, say, if the a was a 3, we would go over one critical point. Instead of going up 1, we would go up 3. Does that make sense? Or if that was a 1/2, we would go, we would start in the middle there, we would go over one critical point, we go up a 1/2. That's where we're gonna see the vertical stretch and shrink. We're still gonna get our period by taking, instead of 2 pi divided by b, we're gonna get pi divided by b. We'll determine our critical point. We're gonna still factor to find the starting point. The starting point in the case of a tangent is gonna be in the middle. The starting point in the case of a cotangent is gonna be, we're gonna start with an asymptote. We'll still have to figure those critical points, and from that starting point, we're still gonna have to get kind of 5 markings on here. So in the case of a tangent, we're gonna go 2 to the right and put our asymptote, 2 to the left and get an asymptote. In the case of our cotangent curve, we're gonna start with an asymptote, 2 to the middle is gonna be our middle part, and then 2 more critical points will get our ending asymptote. And then the translation D is gonna be what's the y coordinate gonna be of that middle point? Okay? Let's give it a shot. This should be fun, don't you think? You don't have to answer that, that was a rhetorical question. Okay. And we're gonna do more of this tomorrow also. Okay, so we'll do y equals 2 tangent of pi over 4x minus pi over 4 plus 1. What are we gonna do first?
Find the period.
So we gotta factor first.
Oh, gotcha.
Okay, so we're gonna make this y equals 2 tangent. We're gonna factor that pi over 4 out, and what's gonna be left behind is negative x minus 1. Okay? Now we're gonna figure out our period. So the natural period of pi, of tangent, is pi, divided by the b, which is pi over 4, is gonna give us 4. So our tick marks, the spacing between tick marks, is again gonna be every 1/4 of a period. It's gonna be every 1. Is that okay?
Is that 1 radian?
Yes, that is in fact 1 radian. Okay. So, starting tick mark is gonna be 1 on the x. So there's 1. And we are going to, where does that start for y value? So remember, tangent starts in the middle. So in the middle for us is gonna have a y value of also, all right. So then I was gonna go 2 two tick marks to the right to get an asymptote, two tick marks to the left to get an asymptote. And then plot the highs and lows, and it's gonna rise from left to right. More to come, more to come.